All right, so hello everyone. How is everyone doing? I hope everyone is good. Today I'm back with yet another video of learn any topic and level up in 20 minutes. So we're gonna be doing segment trees today, and I know that people would click off this video by hearing segment tree, but just to take you all with me, segment trees are very fundamental, and they do not involve any complex or mathematical thinking, nothing like that. They're actually pretty simple, very straightforward data structures like anything else, like binary trees or something like that. So we're going to be breaking down every single thing that segment tree can do, and the time and space complexity required to represent a segment tree, and then query from a segment tree. We're going to be seeing all the proofs. We're going to be seeing the use cases of a segment tree, and what exactly is a segment tree, and how to recognize if a problem is solvable from a segment tree, right? So we're going to be doing that all today, and I'm making this especially for all the newbies out there. So please don't click off this video. I would highly advise you to stick to the very end, and then if you stick to the very end and not understand, then that would be my fault. But yeah, do the full screen thing, take your notes, and stick with me through the to the end of this video. So yeah, let's go. Okay, so we're gonna be beginning with what are segment trees. So as the name says itself, ki this is something like a segment on trees, or trees on segment, whatever you want to call it. Like we have the segment tree is nothing but a binary tree where each node represents an information about a segment, right? So I have written that down here. What does the name tell you? Segment tree, what does the name tell you? So the name tells this is a binary tree, right? This is a binary tree where the binary tree that we were like, if you'll go to LeetCode and solve problems of binary tree, then each binary tree has three things. One is what is the value, so dot val. Then there are two things. One is the left pointer to it and the right pointer to it, right? So like every node of a binary tree has three things, but segment tree, like it's the same thing, but instead of having the left and the right pointer and the dot val, it stores some information about a segment, right? So like if you'll see that I made a segment tree over here. So if you'll see, this is the root node, right? The top one is the root node. Okay, so you can see that the the root node stores the information from the first element of the array to the 8th element of the array. So in case if we had an array of size 8, right, this is our array of size 8. So 1 2 3 4 5 6 7 8. Okay, so now let's say okay, so we'll take that later. So the root node, this node stores the information. Information here means whatever we're building a segment tree on, that is essentially information. We'll get to it shortly. So like for now, just remember the root node stores the information for all the elements of the array. The left pointer stores the information from 1 to the 4th element. So like this part, left part, and the right pointer stores the information from 5 to 8, right? So this part, okay, this part. And then similarly we break that down into two smaller and smaller parts, right? So 1 to 4 again gets broken down into two children, that is from 1 to 2 is its left children, and 3 to 4 as its right children, right? So 1 to 2 is represented over here, this thing, and 3 to 4 is represented over here as this node, right? And then that is broken down again. So we do this until and unless we obtain a single element at the very end. So you'll see that in this particular level that we have only one single element. So yeah, when we encounter a single element, then we can stop our propagation, or we can stop dividing our node into two halves, right? So essentially the height actually is like where every node is being split into two halves. So like this is like it had two children, so we split the first node into two child. Then this node split into two, and this node is split into two. So this was like there was one node in this level, there was two nodes in this level, there were 4 nodes in this level, and there are 8 nodes in this level. So this is like 2 to the power, right? This is 2 to the power 0, this is 2 to the power 1, 2 to the power 2, and 2 to the power 3, right? This is similarly, if we go even further, then this would be 2 to the power 4. That would be like 16 nodes in this particular level, right? So that is what I'm saying. So essentially we are dividing this particular segment or this particular range, that is from 1 to 8, into smaller and smaller halves until and unless we obtain a 1, right? So that is basically like 2 to the 0 plus 2 to the 1 plus equals to 2 to the x, right? And we do this until and unless this is exactly equals to n, something close to this, right? So we can see that the number of 2's that comes over here will be log n, because this is like increasing in terms of power of 2, right? So 2 to the power 0, then 1, then 2. So this is like exponential, it is increasing exponentially. This is like binary search, right? So when we were binary searching, we find a mid, then we see if the, you use a checker function. If the by using that checker function, we either eliminate the left half or either eliminate the right half, right? So essentially we keep breaking the subspace into two parts, and then we go to one part. So that is what is exactly what we are doing over here, where we are splitting into two until unless we get one over here, right? One node, single node. So that is why the height of this tree would be log base 2 of n plus 1. You can see that log base 2 of 8 would be 3, and then plus 1 is 4. So this has 4 levels, right? 1, 2, 3, and a 4. So that is what our upper bound would be for the height of the segment tree, right? So this is like the height of the segment tree. Also, like you would have studied that in the binary tree videos, that when we are creating a complete binary tree means where each node has exactly 2 children, right? Each node has exactly 2 children. So it cannot be 1 or it cannot be null. It has to be 2. So when it is something like that, then the height of the tree is log base 2 of n plus 1, right? So that is exactly what we are doing over here with the segment trees. So hope you got it. Let's move further. Okay, so now we are going to be seeing a segment tree. Why we need to use the segment tree? Let's see a problem. Okay, so let's read this problem. We have been given an array ARR of size n. So basically we have been given an array of size n. We are also given two types of queries. So we have been given two types of queries. First type of query is we can update I of x, and second type of query is sum from L to R. So for the first type of query, this mentions that, let's say if I had an array, let me choose another pen. So like if I have an array of size 4, I'm only considering power of 2 for now. We'll see why, but yeah, let's see. So like let's say our array was 4, 8 or 9 and then 2, maybe something like that, and then update of I of x. So update of I of x, so let's say update of 3 to 8, 3 to 6, let's say. So I of x means in the array update the ith element. So like this, I'm taking 0 based, or let's just take 1 based indexing. So 1, 2, 3, 4. Okay, I'm taking 1 based indexing. This is my array ARR, and these are my indices. These are the values of those particular indices, right? The update of I of x says go to the ith element of the array and update that with the x value, right? So I go to third index. So third index is this particular element, and I update this with 6. So I update this with 6. Cool. Now the second type of query is we need to find the sum from the range of L all the way up to R. So second type of query could be, let's say, find sum from 2 to 4. Let's say we have been given 1 based indexing for now. Okay, so we need to find sum from 2 all the way up to 4. Okay, so now we'll begin with 2 and we'll go all the way up to 4. Now we need to find the sum of the elements of the array such that we have latest changes. So like we might have multiple updates before the sum, and when I take this sum will actually print the latest elements of the array. So like we updated the third index with the value 6, and now when I you get a query of sum from 2 to 4, I add 8 plus 6 plus 2. Okay, so this is like 16. So I return 16 as my answer, not 8 plus 9 plus 2. I do not do that. I take the latest array as my answer. So we need to solve this problem, and let's say my number of queries that have been given are 10 to the power 5, and the size of the array, that is n, is also 10 to the power 5, right? So like for every query, like in the worst case, for every query we need to find sum from 1 to n, then the time complexity of this or of a brute force solution would be order of q into size of n. Like if I'm implementing a brute force solution, right, for each sum query I iterate from L all the way up to R and take whatever is stored in the array. So that is pretty straightforward approach. Whenever you see an update query, just update the third element with whatever is the x value, right? And then whenever you get a sum query, start your iteration from L, that is from 2 to the all the way up to R, and then add all the elements between it. So in the worst case, that complexity could be q into n. So this will throw a TLE, big fat TLE in this case. So we cannot probably implement this, right? This is like a naive solution, brute force solution. So for exactly for problems like these, we can use a segment tree for the exactly problems like these, right? So now we'll see how we can use a segment tree over here, right? Okay. Cool. Okay. So like, okay. I'm considering another array. I'll write the indices over here and the values like 8, 4, 2 and 1 maybe. Okay, this is my array. Cool. Okay, so now I build my segment tree as the last nodes. If you'll see the last particular nodes, the deepest nodes, they only store information from a single node to that node only. So this stores information from 1 to 1, this stores information from 2 to 2. So like I'm building a segment tree for sum now. Okay, I'm building a segment tree for sum. That means if I'm at this particular node, then if I'm at this particular node, then I'll have the information as what is my sum from first index all the way up to fourth index. If I'm at this particular node, I'll have the information of what is my sum for if I begin with the first index and go all the way up to second index. So that is how exactly I would build my segment tree. So now I can start filling my segment tree values from the deepest nodes. Why? Because when I go to this particular node, I actually need its children value, right? So when I go to 1 to 2, I need what is my answer for 1 to 1 and what is my answer for 2 to 2. Then I could just add whatever is x and whatever is y. Then this would be x plus y, right? So we need to process this element after we have processed its children, right? That is exactly why we begin our iteration from the deepest nodes, right? Okay. So now 1 to 1, our answer is 8. The sum from 1 to 1 element, so this is 8. Our answer for 2 to 2 would be 4. These are like array elements only. Okay. So now when I'm at 1 to 2, I check what is my sum from range 1 to 1, what is my sum for range 2 to 2. 8 plus 4 is 12, so I get a 12 over here. Now 3 to 4, what is my answer for 3 to 3, what is my answer for 4 to 4, which is 2 plus 1, which is 3. Okay, now I need to find the answer for the root node. Like what is my answer when I begin from 1 and go all the way up to 4. So what is my answer when I begin from 1 and go all the way up to 2, that is 12. And what is my answer when I begin with 3 and go all the way up to 4, which is 3. So my answer is 12 plus 3, which is 15. So now I have constructed a segment tree. We are only seeing the theoretical. We'll see the implementation, how we'll implement this. Okay, so now we have implemented this. Now we'll first see how exactly would we process update queries. Okay, so like our first query is, let's say, this query where we need to update the fourth element with value 10. Now how would we exactly process this query in our segment tree? Let's say we have constructed a segment tree. Okay, so as we start iterating from the root node, this root node stores the information from 1 all the way up to 4. I find what is the mid. So mid is like, this is then even length. So let's say the mid is 4 plus 1, 5 by 2. So mid is 2. Okay, so I check on which index I need to update it on. That is fourth element, right? So mid is 2, so that means this particular thing remains as it is, because mid is 2, right? And from 1 to 2 our answer doesn't change, our answer only changes for 4, right? So that is, this part changes, right? But this will remain as it is. So I'm seeing, let's say this is my IDX. Okay, so now I'm seeing if my IDX is greater than mid or smaller than equals to mid. If it is smaller than equals to mid, then I can just, or if it is smaller than mid, if this would if 4 would have been 1, then I would have probably moved over here. But since this is 4, so then I'll eliminate my left half and move to the right. So essentially now we'll move this pointer over here. Now 3 plus 4 is 7, by 2 is 7 by 2 is 3, so mid is 3 now. This is mid, m equals to this and m equals to this. Okay, so mid is 3 and I need to update the fourth index. So m equals to 3, the index that I need to update on is strictly greater. So greater things are stored on the right, so eliminate the left and go to the right. So we'll go to the right, and now we'll see ki the range that it is processing is equals to the element itself, right? Because we need to update a single element for now. We do not need to update a range. We need to update a single element at a single which is presented at any index, right? So I'll go to the deepest node, the bottom node, which only has that particular element. So this was previously 1, right? So I'll update this one with the element with the value x. So x was 10 over here, so this is 10. And now I'll do a backtrack. So I move back, I move over here. Okay, now I see what is my latest left and right children's value. So latest left children value is 2 and latest right children value is 10. This has been updated to 10. Cool. So now what is my sum? Sum is 2 plus 10, which is 12. So sum, my part, this is 10. This gets updated to 12. Now I move my pointer one step above. Now I see what is my updated left and right value. So this is 12 plus 12, which is 24. So update this thing to 24. And now I stop my iteration because I have reached the root node. Okay. So that is how exactly how I process update queries. I can keep processing update queries like these, right? And since the height was log base 2 of n, and we are only iterating ones to the bottom and ones to the top, so this is 2 log base 2n. So that is essentially just log base 2 of n. So log n is the time complexity for processing update queries. Okay. Okay. Now we'll see how we'll process the sum queries. Before that, let's assume a case कि the queries that we have been given in the sum are exactly what are present in our segment tree nodes. So I'll explain what I mean by that. Okay. So my segment tree nodes have value for this particular segment, this particular 1 to 2, then it stores information from 3 to 4, it stores information from 1 to 1, from 2 to 2, then from 3 to 3, and then 4 to 4. These are exactly like the information that we store in a segment tree. So we store information of 1 to 2, 3 to 4, 1 to 4. So that is what I've written over here, right? Exactly all the information that we store in a segment tree. Okay, I'm just explaining that. I'm just explaining this theoretically, by the way. Like, please consider this theoretical. I'm just trying to break this down for you. So okay. So now let's imagine the sum. Let's say our sum query has parameters L and R, and these L and R parameters are exactly bounded or guaranteed to be one of these particular thing. So it could either be 1 to 4, it could either be 1 to 2, 3 to 4, 1 to 1, 2 to 2, something like that. In the real world case, this will not be true, because we can be given queries like 1 to 3, right, which is not over here, or like 2 to 4, which is not over here, right? We could be given, possibly, why not? But for now I'm saying ki let's just imagine this particular case. Cool. Okay, so let's say we have been given a query of 3 to 4. Okay, so now when I'm at 1 to 4, I'll explain this more clearly. So when I'm at 1 to 4, this particular root node, this stores information for all the particular elements, but I only need the information from 3 to 4. So I only need the information for 3 to 4. So we have extra information in our root node, right? We don't want the extra information, we only want the information for 3 to 4. So that is why we make two calls, 1 to 2 to the left children, and to 3 to 4 to the right children. Okay, so now we make two calls. Okay, cool. So now we have two calls, one is for 1 to 2, this one, and one we have for 3 to 4, this one. And I need to find the information for 3 to 4. So now when I'm at 1 to 2, I see that this is a completely what do we call it, disjoint segment. What we need to find, the information what we need to find is completely irrelevant to where I am at. So let's say this was 1 2 3 4, and I need to find the information from 3 to 4. So when I'm at 1 to 2, that is at this particular node, then this information is useless, right? We need to find from 3 to 4. 1 to 2 doesn't matter. So like we'll return a 0 from here. Return a 0. Cool. So we'll return a 0 from here because it doesn't matter. And then from when I'm at this particular thing, things completely overlaps with what we need to find. So we need to find from 3 to 4, and we are at the node which stores information from 3 to 4. That is this particular node. So now return whatever is present inside this node, that is 12. So this will return 12, and this has returned 0. So 0 plus 12 would be 12, and then our answer would be 12. So that's how we can process these sum queries when this is guaranteed to be this thing. But obviously this is not guaranteed, and we'll see how we can process when this is not guaranteed. Cool. Okay. Okay. So let's say now I've been given query from where I need to find information from 1 to 3, or let's say this one 2 to 4, because this is a little complex. So like this is my array. I need to find information from 2 all the way up to 4. Cool. So I need to find this thing. Cool. Okay. So when I'm at root node, I see this stores extra information. We don't want extra information, so make two calls, one to the left and one to the right. So left call gets this value, and the right call gets this value, 3 to 4. Now we see right call has the information which is completely overlapping with what we need to find. We need to find for 2 to 4, and this node has information from 3 to 4. We want the information from 3 to 4, that is we want the complete information. So we'll return whatever is present over here. So 12 is present over here, so this will return a 12, because we need to find exactly what is the information, right? We want to find 3 to 4 whatever is present over here, because this thing and this thing completely overlaps. Cool. So this returns 12. Now when I'm at this particular node, that is 1 to 2, you'll see this partially overlaps, but this doesn't completely overlap. If I directly return from here, this will store extra information that I do not want. This is the extra information that I do not want, right? I want from 2 all the way up to 4. I have processed 3 to 4, right? So now I don't want from 1 to 4. I only want to this particular thing, right? 2. So this stores extra information. That is why we make two calls again from this particular node. So when I make two calls again, now our values look like this. Now for this particular thing, that is exactly this node, we see that this information and the information that we need to find from 2 to 4 is completely disjoint. We don't care what we have over here, right? We only need to find what is from 2 to 4. So this returns a 0. This returns a 0. We don't care about it. Cool. When we go to this part where this is 2 to 2, this completely overlaps with this. We need to find what is there, what is completely inside the segment what we need to find. So this is completely overlapping. So this will return a 4, and now 4 plus 0 is 4. So this will again return a 4, and then 4 plus 12 is our final answer, which is 16, which you can see is 16. 10 plus 2 plus 4, this is 16. So now indeed my query is right. I've processed both my sum and update queries very efficiently, and this is how exactly how a segment tree would work. So I've broken down this problem. I tried to give my best. If just in case if you didn't understood it, I would highly advise you to skip back, go back and watch this part again. But essentially the three parts that we care about is key if we need to find information from L to R. This is my query, and I'm at a node which has information from L dash to R dash, and this at which node I'm on, right? Like I'm on a node which stores information L dash R dash. So this thing is completely inside L and R. So if it is completely inside, it doesn't make sense to break it down further, right? So just return whatever is present over here. So I return whatever is present over here. So this is the first type of case. Now second type of case would be, okay, I need to find whatever is present from L to R, but the node that I'm currently on from L dash to R dash is completely outside this particular thing. So if it is completely outside of this particular thing, then we don't care about it, right? This is extra information. I don't want that. So if I don't want this, just return a zero. Return a zero. Or if we were building the segment tree for minimum elements, so let's say this stores the minimum element from 1 to 4. We're storing some right now, but we could do this for all particular very many things. This stores minimum from 1 to 2, this stores minimum from 3 to 4. Then I cannot return a 0 over here, right? So we can return an integer maximum from this for this particular case, because that wouldn't change our answer, right? Integer maximum wouldn't change for min queries, and for some queries 0 wouldn't change. So that is called an identity element. So we need to find identity element. Identity element, in other words, is the element from which doesn't change our answer. So whenever I take an operation with the identity element, it doesn't change my answer. Okay, so now the third type of query would be, coming back to our topic, ki this partially overlaps. So we have seen the complete overlap and the complete disjunction. Now this is a partial overlap. If this is a partial overlap, then we have some extra information and some important information also. So like from here to here is extra information, and from here to here is our important information. So when I'm at this particular node, I make two calls, one to the left and one to the right. When I make two calls, right? So when I make two calls, this is essentially my midpoint. Let's say is somewhere over here. It can be over here. We'll just see where this is going. So let's say this was my mid. So now my two parts would be L dash to M and M plus 1 to R dash. M plus 1 to R dash. Okay. So this is like when I broke this down further. So this thing M plus 1 to R dash lies completely inside. So we can just return from here. But for this thing, this again partially overlaps. So this will be again divided into two parts, but this will return from over here. This will not make two calls. This lies completely inside this, what we need to find. Cool. So I hope you get this. Also the mid can lie over here also. Okay, so in that particular case, let's say this was my answer. Okay, this is lying completely inside, so I return from here, and this is lying completely outside, so I return 0 from here. In the best case, the mid could be exactly the breaking point, or the mid could lie over here also. So these are the only three possibilities that mid could lie. So if the mid lies over here, then this part of information is extra, so we'll return 0, because this and this do not intersect, these are disjoint, so we'll return 0, and this will again have a partial overlap, so again it will make two calls. So essentially at each particular node it cannot make more than two calls. So when I'm at this particular node, it cannot make more than two calls. So in total I'm claiming that for each particular level we cannot make more than 4 calls. So this node can make up to 4 calls, up to 4 calls, and up to 4 calls. It cannot make more than 4 calls, because when I'm at this particular node, it can either be one of the three things, like 3 scenarios. If it lies completely inside, then this doesn't make any call. If this lies completely outside, then also it doesn't make any further calls. It returns 0. It returns whatever the information is stored, and this is the only case that we need to care about. So we have seen all the 3 case scenario where the mid lies. If the mid lies to the left, to the middle, and to the right, in all of the 3 cases, it in the worst case make 2 calls, and that is exactly how, like, it makes 2 calls, and the 2 calls that it makes will never again make two calls again. So like this nodes make 2 calls, and it wouldn't be ki this node also make 2 calls and this node also make 2 calls. Either we'll have information for this node or we'll have information for this node, this particular node, and we need to process this thing. This is what exactly I've described over here. In case you do not understand it, please go back and watch it again. Highly recommended. Cool. Okay, I hope I explained it, like you got what I meant by it. So that is exactly why for update queries also, for update queries we'll need order of login time, and for some queries also we can only have 4 calls for a particular level. Just take a pen and paper and try to prove this yourself. So 4 into login just, so for the update query or for the sum query as well, we cannot have more than login complexity. So for both update and sum queries we have login complexity. So for each query the total complexity would be, for each query I make at most log base 2 of n calls. So this is like q into login, and that is how exactly how we optimize our solution from this brute force solution of q into n to q into login. So that is exactly how a segment tree would work. Now we have already discussed the time complexity. Let's just see how we'll represent a segment tree in memory. So like if you would have solved the problems of binary tree on LeetCode, this is something given in LeetCode, right? Like the class of node, it has 3 things. One is the data that it currently holds, then it has 2 pointers, one to the left and one to the right. So that is exactly how a binary tree is implemented in the LeetCode specifically, right? So we can implement our segment tree also like this. He stores the data of current node and then I'll point it to the left and point it to the right. We can do that, why not? But most people what most people do is we implement this via an array by using an array. Okay, so if we use an array to represent a segment tree, you must have seen this in the trees thing. If this is my node and I need to this is specifically used in heapify, if you know about heapify. So if this node is stored as at index I, then its left children would be stored at 2i plus 1 and then right children would be stored at 2i plus 2, specifically for 0 based indexing. If you're taking the 1 based indexing, then you can take 2i and 2i plus 1. It doesn't really matter which indexing you choose. So yeah, I'm taking 0 based indexing for now. Okay, so if this particular node is stored in ith position in the array, then my left node is stored in 2i plus 1 and my right node is stored in 2i plus 2. Cool, I hope you got it. So now if I need to build this segment tree, this root node will be stored at, let's say, 0. This will be stored at 2 into 0 plus 1, which is 1. This will be stored at 2. This will be stored at 3. This will be stored at 4, 5 and 6. Cool. This is how our segment tree would be storing information. The 0th element stores the information from the first element to the 4th element. The first element in the array stores the information from first element to the second element, right? So similarly. So now what would be my array length, so that I can represent my segment tree without any segmentation fault running out of memory errors, right? So yeah, one case could be what if our array is not a power of 2. So like the array that I'm dealing with, the size of the array is 5. So 1 2 3 4 5. So this is not a power of 2. So this will not form a complete binary tree, right? So only the complete binary tree can be represented like let's say this last column this last particular level represents the total number of elements in the array, right? Because this stores the information for 1 2 3 4, right? So this stores how many nodes are there in my in my array. So if this is a power of 2, then the binary tree would be complete, right? So for 4 it would be complete, for 2 it would be complete, now for 8 it would be complete, like this thing, this thing and this thing, right? For 8 it would be complete. Okay, but if it's not a power of 2, then how would we form our segment tree? So like this and this, like let's say I have 5 nodes in the bottom layer, the bottom level. These are my 5 nodes. Okay, so 1 to 1 and 2 to 2, 3 to 3, 4 to 4, stores information from 5 to 5. Now this is not a power of 2, so this is not a complete binary tree, so this will cause issues, right? when I'm this node will be like alone, so we somehow need to make this a power of 2. So what we do is we round this to the nearest power of 2 which is greater than this. So the nearest power of 2 which is greater than is 8. So I create 3 dummy nodes. I'll choose another color. I'll just erase this thing. So I create 3 dummy nodes for now with identity element which we just discussed. So for the sum query, identity elements could be 0 because this doesn't affect my answer in any way. For minimum queries, that could be integer maximum, int max, right? This wouldn't change my minimum, right? For XOR also it could be 0 for processing XOR queries, right? So this the dummy nodes that I create will be initialized with the identity elements. So now I can create a complete binary tree. I can create a binary tree as this thing, or a segment tree as this thing. And now I create my segment tree as this, and finally like this. And this will store all the relevant information completely exactly the way we want it. So the proof goes as for finding the total space required to represent a binary a segment tree, what we can do is let's just see one thing. If I have a complete binary tree, then there are n nodes. N is the size of the array. N nodes in the bottom layer, right? So if there are n nodes in the bottom layer, then there would be n minus 1 total that are above. This is like I have 8 nodes in the bottom layer, then I will have 7 nodes total from the first node to the one level above this. So this is like 4 nodes in this level, 2 nodes to 6 and 1. So these are like 7 nodes in this level, and there is like 8. So this is like n plus n minus 1 are the total nodes that my segment tree would have. So this is like 2n minus 1 node. So this is 2n minus 1 comes after I have rounded down this to the nearest power of 2. So this could be very long also. So like I have a size of array as 17. So to round it to nearest power of 2, this would be like 32. So it is like almost double. So there is a mathematical proof that if you double the element, then the nearest power of 2 has already been occurred. So 17 times 2 is 34. So 32 is greater than 34. That means I could already make the elements that I want is, and I'll have some extra space, but that doesn't matter. So that is like 2n. I do a 2n to round it to nearest power of 2, and I do 2n minus 1 again because there are n minus 1 nodes. So I multiplied this by 2 again. So this is like 4n. So that is why everywhere you read the segment tree would contain the size of the segment tree would always be 4n. I hope you got it. I definitely hope you got it. If you didn't, just in case, please watch it again. Okay. So isn't it a cool data structure if you have learned till now? And I probably hope that you got what I'm trying to explain, and you're thinking that this is a very cool data structure, because I definitely think this is a very cool data structure. This is my favorite data structure, by the way. So yeah, this is like everything that you need to know about segment tree. We discussed what exactly a segment tree is, how we'll process its query. We discussed the time and the space complexity required to process queries and represent a segment tree. Yeah, we saw that how the update and other sum query would work, and then you can solve a hell lot of problems by using segment tree. So I hope this comes handy. Also in the description I'll attach my template for segment tree along with some good problems. So yeah, I hope it becomes handy. Before seeing the implementation, you can probably do this as your homework. We solve the problem for processing some queries from L to R. You can do that for XOR also. So we have been given 2 queries, one for updating the element and finding the XOR from range L to R. Then for minimum, which we discussed, for maximum also. So this is your homework. You can do this for these 3 things also. And yeah, I'll link some good problems in the description. Now on to the implementation part. So this is like I'm creating a class of segment tree. This is a C++ implementation, by the way. I'm creating a vector of long for tree, and then in the constructor I initialize the size of the tree as 4 into n, which we just discussed, and then I called the build function this build function essentially starts from the bottom, which we discussed. It starts filling from the very bottom, very deepest layer. So it's it finds the mid. It makes two recursive call, one to the left, so 2 into node plus 1. This current node stores the index of the tree, right? Tree is represented in a array. So like this is my index 1 2 0 1 2 3. So 0 is my index, and 2 into 0 plus 1 would be my left child, 2 into 1 0 plus 1 would be right child. So that is why what is exactly is node. L2R is the range, right? So L2R would essentially be what a range is. So when I'm at particular node, L2R is my range. So for root node, this would be from 1 to n if you're taking 1 based indexing, or 0 to n minus 1 if you're taking 0 based indexing. And then if you take a mid and you divide it into two equal parts, one from L to mid, this is my left part from L to mid, so this thing, and from mid plus 1 to R, so this is like mid plus 1 to R, to make two recursive calls for two ranges. This L and R stores if I'm at a particular node, what is the information, for which range am I storing the information for. That is exactly why I use L and R over here. These are just constant. You can store this somewhere also, key for this node, what is my range key, what is my range that I will store my data of. But I've just implemented this by using constant parameters. And then when my L is equals to R, that is only when I've encountered like 1 to 1 and 2 to 2. This would be the only case where our L and R are equal. So when L and R are equal, so then initialize that particular tree node value, so like a segment tree value, with the value of that particular array. So this was array A was my value. So we initialize this and we return from here. And then when I'm at this particular parent, I check what is my left children value. So tree of 2 into node index plus 1, and then 2 into index plus 2, and I add them because I'm processing some queries, and that is what my parent value is. So this is how exactly a build function works. Our update function works just in the same way. We find the mid. I check if this is like where I need to update on I. We were calling update of I and val. So val is what I need to update on. Val is what I need to update of. So ith element has to be replaced with val. So I and val are those, and LR are same thing which were here. So like for this node, what is the segment that it covers, right? That is what L and R are. So I found the mid. I check if the value that I need to update on is in the left or in the right. So if it's in the left, make a call to the left segment, and then if not, then go to the right children. Then when you have L and R are equal, then update the last element, return from there, and then when you're at the parent, just update the parent with the latest children value, which we had discussed over here. Latest value would be updated, and then this will go all the way up to root node. Okay, so this is our update query. Our now query would be like, this is like our disjoint case. So like query L and query R are like sum of L and R. If you want to process L and R query, so this query L and query R are like L and R for processing some query, and node L and node R were like this thing L and R. So like information I'm storing for a segment. So this is like the segment of L and segment of R. So like for which segment am I storing the information, that is exactly what I need. So that is what I'm storing over here. And then node is like the index of like I'm storing the segment tree as my array, right? So node is like my index of my array key, where the node that I'm currently on segment tree, which index it is on in the array. Okay, so like this is the condition for disjoint case. So like if node R is less than query L, so query L is, this is QL query L, this is QR query R, and node L is like the node R and node L is our current segment value. So like if current segment of R is lesser than query L, So like this is current of R and current of L. So if current of R, so current of R, node R is current of R is less than query of L, then this is a disjoint segment. Also this is a disjoint segment. So like current of L and current of R. So like if current of R is lesser than QL, and if current of L is greater than QR, so current of L is greater than QR, then return is 0, because these are like disjoint sections. If this is not disjoint, this lies completely inside. So like this is my current L and current R. So like if current of L is greater than QL, so like current of L is greater than QL, and then current of R is lesser than QR, so current of R is lesser than QR, then this is an overlapping part, so return the whatever the information we have. And then if it is not an overlapping problem and it is not an outer part, then we'll find a mid and we'll make 2 calls. So it will make 2 calls for this thing, partial overlap, and then whatever I get, I'll add both of my answer, and then I'll return my answer. And that is how exactly how segment tree would be implemented. I definitely hope you got it. I definitely hope you enjoyed it. And yeah, I guess we were to take this to 20 minutes, but it had been 45 minutes. So yeah, I guess I'm sorry for that, but I hope you got what a segment tree exactly is. And for the fun part is I'm actually shooting this the second time. I shot it once, but it actually the volume was not recorded. So like I'm recording it again. So yeah, I genuinely hope you got it. And if you have, just in case have any doubt, any queries or any feedback, please do let me know in the comments. And I'm really putting my highest energy for explaining this particular concept. So any feedback would be highly appreciated, and thank you so much for watching. If you learned something, please let me know, and I'll see you guys in the next one. So keep coding, keep working hard, and Radhe Radhe.